We present our work on gradient-less federated gradient boosting trees with learnable learning rates. Federated learning enables the training of a global model using decentralized datasets in a privacy-preserving manner. Existing FPGA research mainly focuses on neural networks. The efforts of developing FPGA algorithms to support other machine learning models, on the other hand, remain unexplored. XGBoost is a powerful interpretable gradient boosting decision tree. In most of the cases, XGBoost outperforms deep learning methods for tabular data on medium-sized datasets and the tensor training examples. In the context of quantitative federated learning, there is a growing need to deploy federated XGBoost on tasks such as survival analysis and financial fraud detection. Current research on federated XGBoost defines two settings. In the horizontal setting, clients' datasets have identical feature spaces but different sample IDs. The central server sends the global models to all clients and then aggregates the updated model parameters after each communication round. In the vertical setting, the concepts of passive parties and one active party were introduced, where passive parties and the active parties share identical sample space but possess different features. As only the active party owns data labels, it naturally acts as a server. Our work focuses on the horizontal setting, and this is the more common one. Although horizontal setting remains to be more common, the training of a horizontal federated XGBoost turns out to be harder. To understand why, we need to reveal the fundamentals of XGBoost. XGBoost is an additive ensemble model. It adapts forward stage-wise regression and consistently learns new trees to fit the residues until a response condition is met. Suppose there are m trees in the tree ensemble, given a data point xi. The final prediction is calculated by summing predictions of all m trees with a fixed learning rate eta. XGBoost is trained in an additive and sequential manner, which means the tree ft plus 1 is trained after the tree ft. And to train a single tree, we first calculate the first-order gradients gi and the second-order hashing hi of all data samples as shown in equation 3. From the root to leaf nodes, the best split can be found by maximizing split scan as shown in equation 2. The split scan at every node is calculated with regards to the sums of the gradients and hashings of the data samples partitioned into the left and right branch based on the splitting point's feature condition. So why is horizontal federated XGBoost harder? This is because finding the optimal split condition of a single tree depends on the order of the data samples as we see in equation 2. We iterate the feature sets and partition the data samples into left and right according to the feature constraints. Therefore, as all clients share the same simple IDs in the vertical setting, the passive parties only need to send the order of the data samples to the active party without revealing the actual values of the gradients and hashings. However, since the simple IDs are different across all clients in the vertical setting, in another word, the instance set ij on each leaf node defined in equation 3 is decentralized. At every splitting point, each class needs to transmit the gradient hashings and sample splits based on feature values to the server to find the optimal splitting condition. And only in this way we can know the partitioning of the data samples into left or right for each client's unique simple IDs in order to calculate the global GL and HL as well GR and HR required by equation 2. Consequently, we identify two key problems raised by this vanilla approach. The first is per node level communication frequency. The server needs to communicate with all clients at every splitting point. We denote the depth of each tree as L and the number of trees in the tree ensemble as M. The number of nodes in the tree ensemble can scale up to m times 2 to the power of L, and so is the number of communication rounds. As a trained XGBoost model is common to have a depth of 8 in 500 trees, the number of communication rounds can reach 100,000. Moreover, in a real application of federated XGBoost, it is possible for a server to conduct more than one round of communication per node and carry out extra cryptographic calculations. Thus, the high communication overhead makes it difficult to deploy horizontal federated XGBoost for practical uses. The second is shared privacy concerns. The sharing of gradients is proved to be dangerous in the previous works. As the training data can be reconstructed using gradients, such sharing needs to be protected. In this work, we ask the fundamental question if it is possible not to rely on the sharing of gradients and hashings to construct a federated XGBoost. In this way, we can simultaneously boost privacy and disentangle the per node level communication frequency. We find this to be possible by formulating two important insights. The first one is as the local datasets of clients can be heterogeneous in the horizontal setting. Using a fixed learning rate for each tree may be too weak, since each tree can make different amounts of mistakes on unseen data with distribution shifts. Consider this example. We have an XGBoost model with m trees. The XGBoost model is trained on datasets for a regression task. We send this XGBoost model to 2 other clients and evaluate it on their respective local datasets. We observe the prediction outcomes of the first 3 trees in the XGBoost tree sample on 2 data samples XA and XB. Their ground truths are equal and both are 100. Since the local datasets belong to 2 clients are heterogeneous, the trees perform differently across data samples. For a first tree F1, it gives a good initial prediction for XB but not for XA. The second and third tree F2 and F3, on the contrary, sufficiently corrects the residues made by the first tree F1 for XA but not for XB. In this case, a fixed learning rate may be too weak because ideally we want a higher learning rate for F2 and F3 on XA, but a lower learning rate for F2 and F3 on XB. The second insight is the heterogeneity causes the trained XGBoost models on different clients' local datasets to converge to local optima that are far away from each other. Consequently, given an AC data sample, these XGBoost tree samples output different prediction results. However, among all tree samples, some can give more accurate predictions because the NC data sample may be closer to an underlying distribution of their trained datasets. Thus, applying a weighted sum on diverse prediction out results given by all XGBoost tree samples can lead to a more accurate final prediction value, helping us to move towards a global optima. It is important to point out that the approach of utilizing weighted sum to converge to a global optima is proved to be effective in the previous literature such as feather averaging and feather prox, as they have given theoretical convergence guarantees for this method. So to facilitate our insights, the final prediction results given an arbitrary data sample with feature dimension d is calculated by a weighted sum of all trees from all clients as shown in this figure. Each vertical tree chain is a tree sample built by one client, where W is the learning rate assigned to each tree, and Zk is the weight applied to prediction results calculated by client case tree sample. We refer to this system as aggregated tree samples, but one question is how to make the W and Z learnable during the training process. We finally make it possible by transforming the aggregated tree samples to a one-layer 1D convolutional neural network. In the first 1D convolution layer, the inputs are prediction outcomes of all trees. The small size CNN is interpretable. The kernel size and the strut of the 1D convolution are equal to a number of trees in each client's tree sample. Thus, each channel of the 1D convolution is the learnable learning rates for a tree sample of a specific client, and the number of convolution channels can be understood as the number of learning rate strategies that can be applied. The classification head, which is a fully connected layer, contains the weighting factor Z to balance the prediction outcomes of each client tree sample and calculates the final prediction result. Here is our full pipeline. Each client first trains its local XGBoost training sample. The server then conducts tree sample aggregation and CNN initialization. After receiving the aggregated tree samples, all clients calculate the prediction outcomes given the aggregated tree sample on their local data samples. The calculated prediction outcomes are inputs of the CNN. It is worth noting that the clients only built XGBoost models at round 1, and the aggregated tree sample is fixed after round 1. For the federated training of the one-layer 1D CNN, the protocol follows the standard FPL algorithm, and we use federated averaging here. The trained global federated XGBoost model consists of all clients' local trained XGBoost tree samples and the global trained one-layer 1D CNN. We name our framework FedXGB-LLR, which means a federated XGBoost with learnable learning rates. FedXGB-LLR brings 2 important advantages compared to the previous methods. The first one is privacy protection. The clients only need to send the constructed tree sample to a server. The sharing of gradient hashings, which may leak sensitive information, is not required. The second is significantly lower communication overhead. The number of communication rounds of FedXGB-LLR is independent of any hyperparameter related to a trained XGBoost and the dataset size. In practice, we find 10 communication rounds to be sufficient for a global federated XGBoost model to reach performance comparable to a state-of-the-art method. For experiments, we benchmark our method against one of the state-of-the-art works on horizontal federated XGBoost, CMFL, which dials locative sensitive hashing in the context of federated learning. We also use the centralized XGBoost trained on the whole dataset as our baseline. We evaluate our method on 6 types of datasets for classification and 4 types of datasets for regression. All datasets have different characteristics and sizes. This table demonstrates the qualitative results of our method. The number of communication rounds is set to 10. From our results, our approach also prompts or reaches comparable accuracy to CMFL and centralized baselines on all 6 classification datasets with 2 clients. For regression, our approach achieves comparable or slightly higher MSE compared to a centralized baseline. For both classification and regression datasets, our method performs better on larger datasets. We hypothesize this is due to the generalization capacity of CNN scaling up with the volume of data. Additionally, as the number of clients increases from 2 to 5 and 10, the performance slightly decreases. We think it is reasonable because the federated learning is harder with more clients. We also carry out two ablation studies. In the left table, we compare the global communication overhead to build a global federated attributes model of approach to our baseline CMFL. Because the communication overhead of our method is independent of the dataset size, we can see our communication overhead is significantly lower, especially as the dataset size scales up. We save the communication cost by a factor ranging from 25 to 700. In the right table, we want to know if the interoperability of our one-layer 1 CNN couples with the high performance. We change the first 1D convolution layer with kernel size and stride equal to a number of trees in each class tree assembled with standard convolution with kernel size 3 stride 1, and the fully connected layer with dimension 256, and remove the flattening layer. From results, our one-layer 1D CNN reaches the best performance on all datasets, although it has the smallest number of parameters in total size. This suggests the effectiveness and interpretability of our CNN model. We find that for all datasets, the performance gap between our interpretable CNN and two-layer fully connected neural network is much larger than the gap between our interpretable CNN and CNN with standard kernel size and stride. Also, the gap becomes larger as the dataset size increases. We argue that in addition to our previous reasoning, it is because CNN can leverage the temporal information across the tree samples built by clients. And our interpretable CNN has the right amount of temporal resolution by setting the kernel size and stride equal to a number of trees in the client's tree sample. That's all for our presentation, and thank you for your time. You can refer to our paper for complete technical details.